For the electronic structure and periodic properties unit, we had to figure out electron configurations for atoms, as well as figure out excited state versus ground state configurations, how to put together the lowest energy electron configuration, the ground state configuration. That's what this question asks. Indicate whether the electron configuration or orbital diagram below corresponds to a ground state or an excited state configuration. So a ground state configuration fills the orbitals in the order from lowest energy to highest energy. And that's that cheat sheet we kind of put together where we drew out the orbitals and we talked about what order we're going to fill those orbitals. So if we start off, got 4p, 4d, 4f, 5s, 5p, 5d, and 5s. I gave you this diagram and said, if we draw an arrow from the upper right to the lower left-hand corner, that can kind of tell us how we're going to fill the orbitals. So we're going to fill the 1s orbital first, followed by the 2s, followed by 2p, followed by 3s, followed by 3p, and here's where we break that numeric sequence, because after the 3p orbital, the orbital next in energy is actually 4s. And then after 4s, then we get to the 3d orbital. After 3d, 4p, and 5s, and the trend continues. So that's the order we want to fill these orbitals. So if we look at the first question here, you can see 3p, we've got the 4s filled, and then they just write this in numeric sequence, but they filled 4s, and then 3d was filled as well. So this would be a ground state configuration because of that. Whereas if we look at the next one you'll see I only have one electron in 5s1, and then I've got 6 electrons in 4d. When we know we should fill our 5s orbital first before going and putting electrons in our 4d orbital. So that would make this an excited state electron configuration. For the orbital diagrams, they're just showing you what electrons are assigned to each orbital and the spin of those electrons. And when we're filling orbitals, we want to make sure that those orbitals have electrons that are aligned, electrons with the same spin. And you can see that they don't have that in this case, which would make this one an excited state configuration as well, because we've got one electron up, and then this electron is down. If we go down to the next question, you can see here they are all spin aligned. They are spin down, spin down, spin down. We want to make sure they're all spin aligned first before we go back and put a second electron in. We want to make sure they have the same alignment when we're filling those orbitals. So we would go through and either put all electrons down, or we would go through and put all electrons up. So that would make this a ground state configuration, because it does just that. It doesn't mix and match what electron is spin up and what electron is spin down. In this module, we also looked at converting wavelength to energy to figure out the energy associated with light. And so we're asked to calculate the energy of a photon, a single photon of visible light with a wavelength of 588 nanometers. And there's 2 equations that we talked about to find energy. Energy equals Planck's constant times our frequency. We can't use this calculation in this case because we have wavelength. And this relates frequency to my energy. There's one other equation that we did cover that we could use. Energy equals Planck's constant times the speed of light divided by my wavelength. We can use this because now we have wavelength and we can relate that directly to the energy of this photon. And this equation is for a single photon of light. One more step before we get started. If we take a look at our constants, right? H, Planck's constant, 6.626 times 10 to the minus 34 joules times seconds. Speed of light, 3 times 10 to the 8th meters per second. That means we have to do one thing with our wavelength before we can use that. We've got to convert it from nanometers into meters. So we need our wavelength in meters. So let's do that unit conversion just to show you. All right, 588 nanometers. We know for every 1 meter, we need a billion nanometers. 1 times 10 to the 9 nanometers. So when we divide across, that brings us down to 5.88 times 10 to the minus 7 meters. Now we can find the energy associated with this wavelength of light. Energy equals Planck's constant 6.626 times 10 to the minus 34 joules times seconds times the speed of light, 3 times 10 to the 8th meters per second over the wavelength of this light, 5.88 times 10 to the minus 7 meters. Unit analysis, right? When we multiply, seconds cancel out. When we divide, meters will cancel out. And that's going to leave us with joules, which is good because we are looking for energy in joules. So if we multiply those two together and divide, we get an energy of approximately 3.38 times 10 to the minus 19 joules, and that is for a single photon of 588 nanometer light. The next question asks you to calculate the energy for 1 mole of photons of visible light, and they want that now in kilojoules per mole. So we have a single photon, so that's step 1. Step 2, right? We've got 3.38 times 10 to the minus 19 joules, and that was per photon. So if we have a mole of photons, 1 mole of anything, 6.02 times 10 to the 23 photons per 1 mole. Photons cancel out. After we multiply by Avogadro's number, now we're going to have the energy for a mole of photons. Multiplying by Avogadro's number gives me approximately 2.035 times 10 to the 5 joules per mole. They want it in kilojoules per mole, so the last step would just be a simple unit conversion. We know there's 1,000 joules in 1 kilojoule, so if we divide by 1,000, that's going to drop this down to about 204 kilojoules per mole. So just be careful. This equation is actually for a single photon. So when we find the energy for a mole of photons, we have to use Avogadro's number to go from a single photon to a mole of photons to determine that energy. The following question 9 asks you to answer these following questions about the orbitals, the subshell of the orbitals, the direction of the orbitals, how many electrons are in each orbital. And we kind of went through electron configuration, but it didn't exactly give you all of these other designating things like L and ML. We did talk about N being the energy level, so I can work through that here. So there are 4 different kind of markers for each electron. There's N, there's L, there's ML, and then there's our magnetic spin. So N is our quantum number, and that's our energy level. L is basically telling us what orbital we're working in. ML tells us the orientation of that orbital, and then the last one is actually, it's MS, it's our It's our spin of the electron. It's either going to be spin up or spin down. So when we're calculating these numbers, right, n is right in the periodic table. N is each quantum level. So n can be 1, 2, 3, 4, 5, 6, and on and on and on and on. L equals 0 to n minus 1. ML equals negative L to plus L. And as you can see, this gets pretty complicated pretty quickly. And at the end of the day, all that I'm interested in is that you can fill electron configurations and figure out electron configurations and not really knowing the N, L, ML. And then the last one is the spin state. It's either going to be plus 1/2 or minus 1/2, depending on is the electron up or is the electron spin down. All right, with that, let's see if we can answer a few of these questions, right? Which quantum number designates the orientation of an orbital? Well, that would be ML. ML tells us the orientation of that orbital. What is the name of the subshell with n equals 5 and L equals 1? All right, well, to answer that, you're going to need some more information. So L tells us our orbital. So when n equals 1, L is 0, right? It can't be anything else. It's 0 to n minus 1. When n equals 2, L can equal 0 or 1. N equals 3. L can be 0, 1, or 2. N equals 4. L can be 0, 1, 2, or 3. When L equals 0, that is our s orbital. When L equals 1, that's our p orbital. When L equals 2, we're talking about our d orbital now. When L equals 3, that is our f orbital. ML gives us the orientation of that. ML can be negative L to positive L. So when L is 0, that's our s orbital. S orbital is spherical orbital. There's no orientation. So ML, right, there's no other values of that. However, if we look at the rest of these, ML for my p orbital can be negative 1, 0, and 1. For my d orbital, negative 2, negative 1, 0, 1, 2. For my f orbital, negative 3, negative 2, negative 1, 0, 1, 2, or 3. And so you can see after doing that, there's our 3 p orbitals. There's our 5 d orbitals and our 7 f orbitals that we have. The orientation shows us how many of each orbital we have. Okay, so back to the question. What is the name of the subshell with n equals 5 and L equals 1? Well, we're on the 5th energy level, and because L equals 1, we are talking about a p orbital, so that would be 5p. If L equals 4, how many values of ML are possible? Well, let's see. If L equals 4, well, we don't really have orbitals beyond f orbitals, so this is purely hypothetical, but ML would be negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, and 4, which gives us 9 possible orbitals we could have. Which of the following is not an allowed set of quantum numbers? So for this one, it was a drop down. It was multiple choice. I had to look and see all the choices. And And of the choices they listed, the one that would be incorrect, they gave you these following numbers: 5, 0, 1, and -1/2. So 5 is fine, right? That's 5 is N. We list them in that order: N, L, ML, and then our spin state. So sure, we can have the fifth energy level. We can have the fifth quantum level. That exists. The next level, L, tells us our orbital. We have an s orbital. That's true. At 5s, we have an orbital there. The next thing tells us our orientation. And they tell us the orientation of 1. And that's where we go wrong, because L corresponds to an s orbital. There are no values of 1. There's no other orientations other than the 0 value. So that's not true, right? In this case, ML is also 0 when we're dealing with an s orbital, because there's only one orientation of it. So it's that third number that would make this incorrect, right? I cannot have any possible other orientations of that orbital. How many electrons are possible in the n equals 2 energy level? So n equals 2. We have an s orbital. That's 2 electrons, and I have my p orbitals. We have 3 p orbitals whenever we have p orbitals. 2 electrons each, so 3 times 2, 6 electrons for 8 electrons total. We can see all of this information in the periodic table as well. All right, so n equals 2. N equals 2 is this row right here. And we can see at n equals 2, I have 1, 2, 3, 4, 5, 6, 7, 8 electrons in that second quantum row. Question 4 gives us the following information. We've got a microwave, and then microwaves use electromagnetic radiation to warm things up. That energy is absorbed by the bonds in a molecule. It increases how those bonds are vibrating, which increases the temperature. And they tell us that it's got a frequency of 2.3 gigahertz. Then they ask for the wavelength, and so I would just ignore this for right now and say either they're asking about a microwave or a cell phone, and I would just keep working with that 2.3 gigahertz because that's what's important in answering this question. So we've got a few different ways to calculate the wavelength. One of the equations I would use, because we've got frequency, is we know the speed of light equals my frequency times my wavelength. We know the speed of light, that's a constant. We're given the frequency, we can use that to find the wavelength of this electromagnetic radiation. And then we're asked to find the energy of 1 photon. So again, we can use that same equation that we used last time. Energy equals Planck's constant, the speed of light over wavelength, or we could just use energy equals Planck's constant times our frequency. We know our frequency, so in this case, this might be the faster calculation. And then the last step, we're asked to find the total number of photons while you're using this microwave or this cell phone. And for that, they tell us that the power is 361 watts. They want to know how many photons does this release in 7.72 hours. And to do that, we need to know one more thing that they don't tell us in this, and that 1 watt equals 1 joule per second. So once we find the total energy per 1 photon, how many joules are there, we can convert watts into joules per second and then basically say, okay, how many photons per second do we need to come up with that energy? So first step first, we've got 2.3 gigahertz, and we need that in hertz, in cycles per second. That as a frequency. So we're going to do a unit conversion first. 1 gigahertz is 1 billion hertz. So 1 times 10 to the 9. So that turns this into 2.3 times 10 to the 9 hertz, which are cycles per second or inverse seconds. So we can write hertz, or we can just say minus seconds, because that's the units we need for the next calculation. So now I'm going to say energy equals, we want to find the wavelength first. So I would say speed of light equals my frequency times my wavelength. We're looking for wavelength, so wavelength is going to equal my speed of light divided by my frequency. My wavelength equals speed of light 3 times 10 to the 8th meters per second over 2.3 times 10 to the 9 inverse seconds. We divide, seconds cancel out, and we're left with meters, which is good because we're looking for wavelength and it should be meters. We divide those two and I get a wavelength of 0.1304 meters. So I would say two significant figures based on the two significant figures there. So I would say 0.13 meters would be the wavelength of this energy. Next, we can find the energy per photon. We know the frequency, and so I would just use that to say, okay, energy equals Planck's constant, 6.626 times 10 to the minus 34 joules times seconds, times my frequency, 2.3 times 10 to the 9 inverse seconds. When we multiply, we'll see that seconds cancel out, and we're left with joules, which is good because energy should be in units of joules. So we've got Planck's constant, 6.626 times 10 to the minus 34. And we're going to multiply that by 2.3 times 10 to the 9, our frequency of this energy. See that we got an energy per photon of about 1.5 times 10 to the minus 24 joules. So that's the answer for part 2, 1.5 times 10 to the minus 24 joules. Now for the last question, we've got 361 watts, and we're going to run that for 7.72 hours. So we know 361 watts is 361 joules per second. That's the total energy that we need, and per second. And we're going to run this for 7.72 hours. So we need also time in seconds so that those units align. So we've got hours, and we know in 1 hour there's 3,600 seconds. So we can get rid of hours and put that information right in seconds. So 7.72 times 3,600. All right, I get 2.779 10 to the 4 seconds. So okay, we run that for 2.779 times 10 to the 4 seconds. Seconds cancel out. We're going to be left with total energy that we need, and we know energy per photon. So we can find the total number of photons we needed to make up this energy. So I'm going to multiply that by 361 to see that our total energy needed is about 1 times 10 to the 7 joules. That's the energy needed. So we have our energy per photon. We can turn that into how many photons we need. Because I know in 1 photon, we're going to have 1.5 times 10 to the minus 24 joules. Because our final answer is total number of photons released. We want joules to cancel out. So joules cancel out when we divide, And we're going to get a giant number of photons, so divide this by 1.5 times 10 to the minus 24 joules. And yeah, we get a huge number of photons. I would say 3 significant figures in this case, based on the power and the hours. So I would say something like 6.69 times 10 to the 30 photons would be needed to make up this energy. So this last part was a little bit tricky because they didn't give you the important information that 1 watt is actually 1 joule per second. And that's the conversion factor we need to go from joules of energy to watts and connect those two to answer that question.